Alrighty, welcome back everyone. So let's pick up where we left off and discuss water. Water, the formula is H2O, and as we discussed in the last video, we were talking about polar bonds. So water itself is comprised of polar covalent bonds because what you have as a result of the formation of the water molecule is you have a partial negative oxygen, which you can see here, delta negative. So it's partial, it's not fully because you have the electrons being shared by hydrogen. And then you have hydrogen, which is a partial positive. Again, it is partial because it's not fully positive because you also have the electrons being shared by oxygen. Okay, so the reason that you have polarity again, remember, is because of unequal sharing of the electrons. So you get this unique bond angle, which is 104.5 degrees, and you get the Mickey Mouse shaped Bohr model for water because you have the electrons in a position where they are being shared. Okay, the second thing I want to discuss from this image right here is the fact that you have the water molecules able to form bonds with one another. They're not really bonds, they're actually weak attractions between one another. And the ability to form hydrogen bonds is what gives water its amazing property, okay? So you can see that we have the partial positive hydrogens attracted to the partial negative oxygen, and that is what results in the hydrogen bonding. All right, so obviously, if you didn't know, which I don't think anybody doesn't know this fact, water is essential. Without water on Earth, life would not exist. Every single living organism on this planet requires water to survive. There's no way around it. So, the ability of water to form hydrogen bonds leads to two very important processes, or what we call properties that water can undergo. And the first property is the ability of water to have cohesion. And what that means is co means the same, together. So water will stick to water. Water molecules stick to water, so you can get this amazing ocean right here. So that's because of cohesion, okay? Adhesion is the ability of water to stick to surfaces. So again, if you've ever sat in a restaurant and you played with your straw, you can cover the top of the straw, and you can see that your drink has moved up the straw. That is capillary action. That is capillary action due to adhesion. Water has a high heat capacity because water has a very high specific heat. It is very difficult to change the temperature of water. And what I mean by difficult is it requires a lot of energy to be able to change the temperature of water, even by 1 degree. So going one degree Celsius takes a lot of energy, and it's the highest specific heat out of all the compounds on the planet Earth. Also, water is a good solvent, which you all know. You can put solutes in it, and again, water is an amazing solvent for drinks, for coffee, iced tea, lemonade, so on and so forth. Another really unique property compared to other substances on this planet is that solid water is less dense than liquid water. Therefore, solid water will float on liquid water. And that is pretty amazing, because when you look at water, water will then freeze from the top to the bottom, as opposed to other substances where they freeze from the bottom up. Now, I'm going to ask a question to all of you. Why do you think that's an important property? Why do you think that's an important property? Think about the history of the planet, okay? Think about what went on in the history of the planet. Well, remember that the planet has gone through several different periods of ice ages. And if water did not have this unique property, that means all the organisms that were in the oceans and lakes and in the seas would have been killed off. But because water freezes from the top down, life was able to continue. That's a very, very important property. All right, there's the capillary action we talked about, cohesion and adhesion. You can see, very important, not just to playing around with your drink. For example, during those awkward moments on a date, but how about for plants and trees? Okay, the ability for capillary action to occur allows water to travel from the base of the tree, where the roots, all the way up into the top of the tree, where the leaves are also getting water. It is pretty amazing. All right. Again, water, because of its high specific heat, okay, that means its ability to resist change to temperature, okay, it aids in homeostasis. That is why you are able to maintain a average set core body temperature. It is because no matter what you're doing, if you're walking outside and it's, for example, the suite's going to be 112 degrees, okay, your body is going to maintain its average temperature of 98.6 degrees. Or if you go to the mountains in the winter and it's minus 15 degrees, again, the same thing. Your body is going to maintain its temperature due to water. So you can see that, again, the way that water aids in homeostasis is by this process that's been thoroughly studied. And basically what happens is heat, which is a form of energy, which we're going to talk about, again, from the sun, because as we're going to learn all the energy from that's found on the planet comes from the sun. So the sun is able to disrupt the hydrogen bonds between the molecules, but then just as they're quickly disrupted, they can quickly reform, and you can see new bond forming. And again, it will not change the temperature of water, as opposed to, hey, let's look at the sun hitting the sand on the beach. Okay, there isn't a lot of hydrogen bonding in the sand, so therefore it gets really hot really quickly, and you all know that feeling, all right? Or walking on a hot sidewalk, especially here in Phoenix. So really, really important property in regards to the fact that water can help maintain our core body temperature and the body temperature of a lot of other organisms on this planet. Okay, again, solutions. So water can be used to form solutions. So what you do is you take a solute and you dissolve it in a solvent, and that's how you have a solution. So definitions, which you should know already. A solvent is something that else that dissolves into it. A solute is something that dissolves in a solvent. Okay, this statement right here, seen it everywhere, heard it since I was a little kid. Water is the universal solvent. Okay, almost all substances on the planet Earth can dissolve into it. Okay, there are substances that cannot, and we're going to talk about those, and those are the non-polar molecules. But if you think about it, the substances that can dissolve in the water are the polar molecules, ions, which you already know, salt, so on and so forth, sugars. And then we have substances that can partially dissolve in water. Okay? So let's talk about polar molecules and ions. All right, this solution is basically what that means is this the ability to be able to disperse in water. So we have polar molecules, and polar molecules, remember, those are the molecules that result from uneven sharing of electrons. When you have a polar molecule, you can describe that molecule as being hydrophilic. Hydro meaning water, phile meaning love in Greek. So it's quote unquote water loving. That means it will interact with water, and then water will surround these molecules, and the molecules can remain intact. Those are polar molecules interacting with water. Ions dissolve in water, but they don't disassociate. So basically, you can take the sodium ion and they can break down, but they're not going to disassociate. Electrolytes, really important to maintain our physiology of ourselves as human beings, but other organisms such as your pets, your dogs, your cats. Okay, electrolytes, basically what occurs is, the reason that we call them electrolytes is they're able to dissolve and dissociate in water, so salts, acids, and bases, but they can also readily conduct an electric current. And that's going to be super important, especially when we get to when you move on and go to 201, when we talk about physiology, and you're going to be able to understand that the ions, sodium and potassium, are super important for electrical conduction via the nerves in your body that will generate the nerve impulses. Okay, we also know that water can be broken down itself, and basically that's going to result in a concept that, again, you've heard of, acids and bases. Okay, so you can take hydrochloric acid, put it in the water and it breaks down into hydrogen chloride, and then it's supposed to be Na, sodium bicarb. So you can take the sodium bicarbonate, put it in water, and break it down to sodium and bicarb. All right. Non-polar molecules. Non-polar molecules, you've seen this before. Again, they do not dissolve in water. Non-polar molecules are described as hydrophobic. Hydro, again, water, phobia, a fear. So they are quote unquote water-fearing molecules. However, again, they're not sentient. So basically, they don't interact with water because of their bond angles. It has nothing to do with being afraid of water, right? So again, it is the fact that you have the equal sharing of electrons that result in, hey, I'm happy just the way I am. I'm sharing my electrons equally. I don't want to interact with water, okay? Just leave me alone. You can pour all the water all around me forever and ever and ever. Nothing's gonna happen. So here's oil and water. You've seen that before. You've seen after a rainstorm, puddles in the parking lot where you can see that slick, shiny, reflective liquid on top of water. That's oil from our car engines dripping on there, dripping onto the parking lot. It rains, water puddles are formed, and they're not going to interact. Think about when you're boiling pasta, you add a little bit of oil in there, the oil is going to float. Doesn't matter how long you boil the water, doesn't matter what you do to the oil, it is going to remain nonpolar, and it is not going to want to interact with water. Okay, example, again, fat and cholesterols, because they are hydrophobic and nonpolar, you're going to learn in anatomy and physiology, proteins are required to transport them throughout the blood because blood is mostly water. All right, antipathic molecules, both polar and nonpolar regions. So this is a phospholipid molecule, amazing molecule right there. You have a hydrophilic head, hydrophobic tail, and basically that is going to result in the molecule having two different properties because of the way it was designed. Neither region will dissolve or it's completely excluded. So halfway in, halfway out. So the polar region will dissolve in water. The non-polar region is going to be repelled by water, which we talked about before. And basically, you're going to take these phospholipid molecules, arrange them in such a way that will result in one of the most amazing structures on the planet Earth, the formation of a phospholipid bilayer, which will then result in the membrane, the cell membrane, which we're going to talk about in great detail in chapter 5. Okay, so with the phospholipid molecules, again, the heads are going to be in contact with water, so they will interact with water. The tails are going to be basically interacting with one another. They don't want to touch the water. And then the bilayers, again, are going to form, and that's going to help protect structures from getting into our cells. So we'll talk about that later on. So here's the creation. And basically, it's a spontaneous formation of the bilayer. It's one of the only times, one of the two times in biology we can use the word spontaneous. And basically, because of water, the phospholipid molecules are going to spontaneously arrange themselves in this way that's going to result in the hydrophobic tails interacting with one another, and then the hydrophilic heads interacting with water. So this is actually a magnified image showing you the phospholipid bilayer, and the phospholipid bilayer is basically the cell membrane. So again, really fascinating. All right, we're going to talk about that a lot later. All right, water mixtures, substances that are mixed are not chemically charged. Substances can be separated by physical means, so we'll talk about that. So you can see suspensions, colloids, and solution. You can take a look at that on your own. Okay, final topic I want to talk about in terms of water, acids and bases. In water, most molecules are H2O. So again, you can split them into hydrogen ions, you can split them into hydroxide ion, and basically that is what's going to result in acidity or again, alkalinity, basically the creation of the pH scale. pH is a measure of hydrogen ions in a solution. So if you have a low pH, means that you're going to have a higher concentration of hydrogen ions and less, or a decreased number as opposed to the hydrogen ions of hydroxide ion, which is acidic. So 0 to 6 on a pH scale is described as being acidic. The neutral pH is 7. And basically what that means is you have an equal number of hydrogen ions and an equal number of hydroxide ions, which will result in the pH being 7. A high pH, so a pH between 8 and 14, results from having a decreased amount of hydrogen ions and an increase in hydroxide ions. So you've probably seen a pH scale before this class, so you can see the different substances, very common substances that you've heard of. For example, on a pH scale, lemon juice and stomach acid between 2 and 3. You can see your urine is 6. Your human blood is slightly above neutral at 7.4, and acids are at 10.5. So again, you can just look at those, and as you go further away from 7 in either directions, the substances become more caustic. That means they can cause more damage to organisms. Okay? So really important are basically substances called buffers, and buffers basically help prevent pH changes. So we have the natural buffers that are produced in our body. They are transported through our blood. They are made in our lungs. Basically, the bicarbonate is the buffer that helps maintain your pH in your blood at a constant of 7.4, your pH in your tissue at basically around 7, your urine basically around 6, so on and so forth, helping to maintain the concentration of your stomach acid at around 2.5, so on and so forth. So there's buffers that are going to help maintain and prevent the pH from changing, because you need to have those pHs remain constant in the different areas that I mentioned, because of something very important we're going to be talking about, because enzymes require specific pHs to function. Therefore, the pHs cannot change in those areas. And we'll talk more about that later on. All right. Any questions about water? Again, please email or jump into the Zoom office hours. And I am going to stop here right now and then pick up next time with our discussion of Chapter 3, Biological macromolecules. All right.